in Poland. Yes. And so we met there during the, I think it was the second workshop on geometry and orders organized by Stefan Felsner and Mütze, and discussed this problem. So this was with Oswin Aichholzer from TU Graz in Austria, Tony Huynh, who is now in Australia, Kolja Knauer in Marseille, Torsten Mütze, who's currently in Warwick, UK, Raphael Steiner from Berlin, and Birgit Vogtenhuber from Graz as well. So what do I mean by flip graphs? So maybe, oops. Yes. So maybe if you've heard of flip graphs, maybe you've heard of this one. This is sort of the well-known flip graph, which is the flip graph of flips in triangulations of a convex polygon, right? So you got this convex polygon, which is a hexagon here, and a flip consists of removing an edge and replacing it by the other diagonal of the empty quadrilateral that it creates. This is a Catalan family. It's a well-known Catalan family. And the flip graph of this structure with this definition of a flip that you can see there is very well studied. It appears in a lot of combinatorics context, combinatorial context, and a lot of different papers, including topology and combinatorics, of course, and computer science. This graph has a property which is really nice, is that it's the skeleton of a polytope that you may have seen before, which is called the associahedron. So I label here the vertices of the associahedron by another Catalan family, which is in one-to-one correspondence with triangulations of a convex polygon, which are binary trees, right? And the edges now of this polytope, they correspond to, so flip in the triangulation, which is also a rotation in the binary tree, which is this local operation that you use to rebalance binary search trees, right? So what kind of questions can we ask on these objects? There's been quite a bit of work on the diameter of associahedra. So what is the maximum number of flips or maximum number of rotations in a binary tree that you have to do to transform any binary tree to any other? Okay, what's the maximum shortest path between two vertices of the associahedron in terms of the number of edges that you have to go through? Okay, this was a question that was asked by Slater and Tarjan for data structures purposes, and it was solved by Slater, Tarjan, and Thurston in a famous paper in 1988. And it is essentially 2 times n, where n is the size of the objects that you look at, right? So the number of nodes in the binary tree, number of vertices in the convex polygon that you triangulate, okay? The proof has been refined by Lionel Pournin quite recently, like 5 years ago. And now we know exactly what is the maximum distance, flip distance or rotation distance among those objects of size n. Now we are interested in the computational question on another kind of flip graph. So the computational problem is, if I give you 2 objects, what is their flip distance? What is the minimum number of flips of those local operations that you have to do to transform the first one into the other, okay? It's known to be NP hard for triangulations of point sets in the plane where you perform those geometric flips, but not for convex point sets, right? For point sets in convex position, this is the flip distance on the associahedron. And that's a major open question. What is the complexity of deciding what is the rotation distance between 2 binary trees or the flip distance between 2 triangulations of a convex polygon? So it's known to be NP hard when the points are, you know, not necessarily in convex position. It's also known to be NP hard for triangulations of simple polygons. Okay, so if you just look at a simple polygon, so a polygonal domain without holes, and you triangulate it, there's a notion of flip there. And computing the flip distance between 2 such triangulations is an NP hard problem. So I'm interested, my motivation for looking at this question is that for the associahedron, there's this natural sort of description or interpretation of the flip distance as a walk on the edges of a polytope, okay? And in case of triangulations of simple polygons or arbitrary point sets, you don't have this nice description. So I'm interested in the complexity of computing flip distances in the cases where this flip distance is actually walk on the edges of a polytope. This transformation can be interpreted as a walk on the edges of a nice polytope. So for matroid polytopes, for instance, this is easy. Think of graphic matroids. You have two spanning trees and a flip is replacing an edge by another. Okay, then the distance there is just the symmetric difference between two spanning trees, right? And this is true for every matroid. And when you do these moves, you walk along the edges of a matroid polytope, right? Or the polytope of the matroid basis. For associahedra are special cases of polymatroids, right? And this question is open there. So it's known to be, associahedra are known to be polymatroids, but I've never seen any discussion on, how to compute the distance on the edge distance on a polymatroid polytope. What about the intersection of two matroids? This was my motivation for looking at this problem of graph orientation. So what am I going to explain, to work on exactly? So we have this definition of an alpha orientation of a graph. So alpha is here a function that maps every vertex to an integer positive number. And an orientation is an alpha orientation of a graph if every vertex V has outdegree alpha of V. Okay, so you just prescribe the outdegrees of the vertices. Okay, so if the vertices have this prescribed outdegree, then this is an alpha orientation for this function alpha. Okay, so very simple definition. And actually, one special case of alpha orientations are perfect matchings in bipartite graphs. So if you look at a bipartite graph and you pick one side of the bipartition and you say that the outdegree there must be 1, and now you look at the other side of the partition and for every vertex on the other side, you say that the outdegree must be the degree minus 1, then what you encode there, every alpha orientation corresponds to a perfect matching in this bipartite graph, right? Because you have outdegree 1 and in-degree 1 on each of the sides, right? So these are exactly the edges coming out of one of the side are exactly the edges of a perfect matching in the bipartite graph, right? So one special case of alpha orientation is bipartite perfect matchings in bipartite graph, and there's a lot of other structure that fit into as a special case of this definition. For instance, Schneider words in triangulations are also free orientations, right? Orientations in which of a triangulation, a maximal planar graph in which the outdegree is always free, okay, for vertices and in the interior of the outer triangle. So many structure, well-known, well-studied structure fit into this definition of alpha orientation, including perfect matchings in a bipartite graph. And now, so I promised a flip graph. So what are those flips now? Now a flip consists of, well, if you want to preserve the alpha, if you want to go from one alpha orientation to another, one operation you can do is look at a directed cycle and flip every edge on this directed cycle, right? Because then the outdegree of every vertex is not changed, right? So you go from one alpha orientation to another, okay? So this is the flip graph on top of my alpha orientation. So, so we look at the graph that is built, for a given undirected graph. You start with an alpha orientation and you look at this, symmetric binary relation that goes from one orientation to another by flipping edges along a directed cycle. Is that clear, the definition? Good. So here's what it gives as a graph for the special case of perfect matchings in the bipartite graph I just showed you before. So yes, okay, let's ignore the dashed and solid distinction for now. You can see that whenever there's an edge between two perfect matching here, it means that there is one cycle that has been flipped. Okay, for instance, to go from this one to this one, you flip the fourth cycle here. Okay, and this is really flipping now alternating cycles. Okay, so on top of the special case of perfect matchings in a bipartite graph, flips consist of picking an alternating cycle and flipping it. Okay, and there's one way to do it, and it's a symmetric relation. This graph here is planar, and dashed edges correspond to flipping cycles that are not faces of the embedded planar graph. Okay, so solid edges here, they correspond to flipping cycles that are faces of the drawing of the planar graph. So with this, we'll come back later to this distinction. Okay, this is what the drawing. But for now, just look at those edges, and every edge there corresponds to flipping an alternating cycle in the perfect matching. All right, no questions so far? Okay, so yes, so what is the structure of this flip graph? Okay, is there a polytope? Okay, well, we can realize that actually alpha orientations are intersection of two partition matrices. Okay, so partition matrix, they just prescribe, you know, the degree. Okay, it involves two sets, right? And it's just saying that the perfect, okay, there are very simple partition matrix such that the intersection of those are alpha orientations. And there's this famous theorem that says that the common base polytope, so meaning the polytope, which is the convex of all bases that are common to both matrices, is the geometric intersection of the two matrix polytopes. And adjacency on this polytope is characterized by cycle exchanges. So it's much easier to see this on the perfect matching polytope. Two perfect matchings are adjacent on this polytope whenever the symmetric difference consists of a single cycle, okay? So this adjacency relation on top of the perfect matching polytope, this is exactly the definition of a flip, okay? So this flip graph is exactly the skeleton of the perfect matching polytope, right? And this, in general, for alpha orientation, is the intersection of two matrix polytopes. So the adjacency characterization is an old result by Balinsky and Rusakov, and the generalization to any intersection of two matrices is due to Frank and Tadeusz, and there's a shorter proof by like 20 years ago by Iwata. So here's what it gives for perfect matchings on the bipartite graph that I showed before. So here you have that you have two perfect matchings, right? And okay, you look at, so one partition matrix is saying, okay, there must be one outgoing edge from the red vertices, and the other partition matrix says there must be one incoming edge to the square vertices, okay, the orange square vertices. Now the intersection of those are exactly perfect matchings, right, by definition. And now if you look at those two and the symmetric difference there, you realize that they form together a cycle. And there's something called the exchange graph for each of the two matrices. And the exchange graph have edges, the solid edges on one side. For one of the partition matrix, the exchange graph consists of the solid edges. For the other partition matrix, the exchange graph consists of the dashed edges. And the union must be a cycle. And this is what determines adjacency on the intersection of the two matrix polytopes, okay? So here is just saying that the symmetric difference between the two perfect matching, right, which is the union of the edges 1, 2, 3, 4, 5, 6, well, that forms a cycle. So you can go from the left matching to the right one in a single flip, which means they're adjacent on the polytope. Okay, is that clear?
Just a question. What if the symmetric difference is not a cycle, but is a union of cycles?
It's always a union of cycles, right? And this is a way to go from one to the other. This is showing in particular that the diameter of the perfect matching polytope is at most, okay, for simple graphs, it's at most n/4, because a symmetric difference induces a collection of cycles which you can flip one by one, and each cycle has size at least 4. Right? So the maximum distance between two perfect matchings is at most n/4, right? Because in the intersection, you must have degree 2. So it's a degree 2 regular graph, right? So it's always, right? Is that right? But when there's only one cycle, then that means you're adjacent on the polytope. Does that make sense? Thanks. Yes, good question. So it's actually always the case. So you may think maybe, okay, this is the next example, right? It's coming up. You may think that, okay, just look at the difference, look at all those cycles and flip them one by one, right? why wouldn't that be the flip distance? Why wouldn't that be the shortest path between the two? Okay, and actually it's not. So let me show you an example. So here, okay, we have this orientation of the graph. It's actually a perfect matching, right? It's also 1 and 2, so it's I could have drawn in class a perfect matching. Let's say we want to flip the orientation of each of the 4 cycles, the 4 rect cycles, okay? Suppose this is my symmetric difference, okay? So I can go through C1 and can reverse the orientation of C1, then of C2, then of C3, then of C4. That's 4 flips. Am I right? So the distance between those 2 orientations would be 4 if we, okay, it's at most 4, right? Because you can always flip those 4 guys. But now look at this sequence of flip, D1, D2, D3, okay? So D1 is this cycle here from 1, blah, 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 and then you go all along. See, it's this phase of the drawing. You see my, okay? So it's going through those vertices and it's flipping sort of half of the C4s, right? Of the 4 cycles in the middle. And then you flip D2, right? Which is the symmetric phase, but below, okay? And now you're flipping the other half of the cycles. So now you're done flipping all the cycles. You've done 2 flips so far, and you're done flipping all the cycles, the 4 cycles in the middle. But now the problem is that you flipped all 4 edges that are on the outer face of this drawing, right? Well, that's 1 more flip, okay? So you can actually flip those 4 cycles here in 3 flips instead of 4, right? So just flipping, you know, the symmetric difference doesn't give you the shortest path always. Is that clear? So now my question is, how hard is it to compute the shortest flip sequence, right? So here's the result, right? It's an NP-complete problem, okay? So given, and it's NP-complete even in a very special case, even when the graph is bipartite, degree at most 3, and planar, and 2 connected. So I give you a pair of perfect matchings in this very special, you know, graph. And I ask you, what's the minimum number of flips, you know, to go from X to Y? And actually, I ask you the following question. Is it at most 2? Can we go from X to Y by flipping at most in a sequence of 2 flips of alternating cycles? Right? So is it at most 2? You can fix actually the distance. So the decision problem is with respect to a fixed parameter, right? So deciding whether it's at most 2 is NP-complete. Is the statement clear? Okay, so a short glimpse at the proof. So this is a reduction from a very special case of the Hamilton cycle problem in which the input graph is planar, it's directed, and the nodes coming, the vertices, yeah, the nodes come in 2 flavors. Either there's 1 outgoing edge and 2 incoming, or 2 incoming and 2 outgoing and 1 incoming, okay? So there's no sink or source. And actually you need that, right? Otherwise you're stuck there. So, so all the vertices, they look like either this one or this one reversed with 2 outgoing edge and 1 incoming. And now the idea is, so let me give you a flavor of this gadget that we use to reduce the Hamilton cycle problem to our problem. So suppose we have this kind of node. The other kind of node is sort of symmetric. There's this very similar gadget that works. And suppose that we have a Hamilton cycle, and I want to show you an instance of the perfect matching flip distance problem, such that, well, given this Hamilton cycle, you can actually do 2 flips and go from one matching to the other. So the gadget is there. The blue edges correspond to edges in the perfect matching X, and the red dashed edges correspond to those in the perfect matching Y, okay? Now, suppose we have a Hamilton cycle. Well, suppose that it goes from this node to this node to this node, okay? The other case, again, is symmetric. So we can go from there to there and down, okay? This is the portion of our Hamilton cycle that goes through there. Then the 2 flips that we'll do will first use this portion of the path to flip this alternating cycle that goes, you know, through the red vertex on the right and then back. This is an alternating cycle, right? It's not blue, blue, not blue, blue, not blue, okay? So you flip it and now those two edges become blue. And this one becomes blue and the two blue edges become red, right? And now you flip a second time, but instead now of taking this detour in the gadget, you go straight. So now those two blue edges become, you know, non-blue again, and this one turns into blue. So you have, once you've done this, those two flips, then you've indeed transformed the perfect matching X into the perfect matching Y, right? You've transferred, you know, you've removed the blue edges and you've included the red edges, right? And now you can do this in the other case too, and then you can go the other direction. But if there's a Hamilton cycle, by going, you know, once through this path and the second time through this other path, well, in two flips, you can flip from one perfect matching to the other, and it's a if and only if, okay? So you can do two flips if and only if you have a Hamilton cycle in the initial graph, okay? This is sort of a short glimpse at the reduction. This is sufficient for completing the reduction. Once you've seen this, you have everything. So deciding whether the flip distance is 1 is easy, right? You just compute the symmetric difference, see if there's a single cycle, right? But deciding whether it's at most 2, that's NP hard. Okay, so in particular, there's a lower bound on the approximation factor, and it's not an FPT problem because we fix the parameter, you know, we flip the decision, we ask, you know, to make a decision about whether the distance is a fixed number, a fixed constant. So there's no Opitz FPT with respect to the distance as a parameter. Any question on that? Let me check time. Okay, so let me mention another problem that we looked at. Suppose that the graph, well, it's NP hard even if the graph is planar, right? If the graph is planar, there's something that we can look at, which is called the planar dual, right? Now, every face of the planar graph becomes a vertex, and every edge becomes now a dual edge that connects two faces, right? So this is how the picture looks like. So the original edges of the planar graph are red, and now I drew the dual edges as dashed green, right? And now let's see what is a flip in this dual planar graph. So a flip, for instance, would flip this red directed cycle. Well, this amounts to considering the cut that is induced by the green edges in the dual planar graph, right? It's a cut that removes, you know, separate those two faces from the other faces, right? So a cycle in the original planar graph maps to a cut in the dual planar graph, okay? And this cut, because the cycle is directed, this cut is directed from one part, all edges go from one part to the other, okay? So in the dual planar graph, flipping a cycle amounts to flipping a directed cut. Flipping the edges on the directed cycle, it amounts to flipping edges in a directed cut. You see this? And now we can play with this duality, right? We have this dual notion of a C orientation when, again, a small c here is a function that prescribes for every cycle in some, say, you know, in some direction along the cycle, you fix the number of forward edges, right? The number of edges you meet that go in the same direction as you, right? So of course, it must be the function C, just as in the alpha orientation, must be consistent with the degrees and the cycle structure of the graph. So you can prescribe it, for instance, only for a base of the cycle space of the graph. But the thing here is that you want to preserve the number of forward edges along the cycles that along all cycles. And actually, this is preserved by this function C. This C orientation is preserved whenever you flip a directed cut, right? So there's a dual notion of what we saw with alpha orientations and directed cycle flips, which are C orientations. A directed cycle flip maps to a directed cut flip. And when in planar graphs, you flip a cycle that forms a face of the planar graph, remember the dashed edges in the flip graph? They were corresponding to flipping faces of the planar graph. Well, that amounts to in the dual planar graph, transforming a source into a sink, right? A vertex in which all edges are outgoing, now you make them all incoming. This is a special case of a cut where you just cut one vertex out, okay? So those Fischl cycle flips in the primal interpretation on planar graphs, they correspond to source sink flips in the dual setting. And now we can ask the question, you know, for any directed graph, what is the complexity of computing the distance between two C orientations of this graph using only source sink flips? Okay, so what is the source sink flip distance between two C orientations of the graph? Okay, so I give you two orientations. They satisfy this number of forward edges, same number of forward edges along every directed cycle, along every cycle in both orientations. And I want to go from one to the other by transforming sources into sinks or sinks into sources, right? This is the question. And now things are better. Now there's a polynomial time algorithm, okay? So because you restrict to those simpler flips, you don't look at directed cuts, you know, of any size, just of size 1. You transform, you know, just do source and sink. Then there's and the reason why there's a polynomial time algorithm is that there's a very nice structure now on top of the flip graph. It is a distributive lattice. So here's how it goes. So you fix a top vertex, which is in red pink here, which we call the top vertex, and you forbid to flip this one. Okay, you say I'm never going to flip this one, and say, okay, I'm not allowed to transform this source into a sink or this sink into a source. Okay, but you can flip any other. Okay, and now you look at this partial order relation that you have, which is you go, you know, one C orientation is above another if they differ by a source becoming a sink. Okay. Yeah, I think this is going, you're going up when you transform sources into sink, and the cover relation is one source is transformed into a sink, you know, and this is a cover relation in your partial order. Then the partial order that you obtain with this cover relation and the transitive closure is a distributive lattice. Okay, so there's a meet, a join, as in the lattice, plus those operations are distributive in both directions. So it's a super well-structured object. And thanks to this nice, so you can see this, right? For instance, if you go from this one, to the top one, you transform this source here, which is the yellow vertex just below the top one. It was a source, and you transformed it into a sink, right? And you can check that this one, for instance, is amounts to this flip here is transforming this source into a sink there. Okay. This is the structure, and then things become really nice, and then you get a polynomial time algorithm. So there's an algorithm that if you give me a pair of C orientations of G and there's a fixed vertex top that you're not allowed to touch, then you can compute the shortest sourcing flip sequence between the two in time proportional to the cube of the number of edges of the graph. Okay, so there's a polynomial time algorithm if you sort of restrict those flips to be those ones in the dual setting. And then what if you bound the number of vertices in your cut? Okay, so we've seen that if we do not bound it, then this amounts to the original primal problem, which even in special cases is NP-hard, which is flipping directed cycles in alpha orientations. What if we allow, for instance, to flip in C orientations to flip cuts that have two vertices on one side, okay, instead of just one. If there's just one, then we know how to compute the distance. But if we allow to flip two at a time, then it becomes NP-hard again, okay? So depending on this notion of flip, we get, you know, we're polynomial when we can just do source to sinks. But as soon as you can do, you know, cuts of size 2 at a time, then it's NP-hard again, okay? So it's sort of another flavor of the same problem, but with this additional constraint on the flips you can make, and this in this case it remains hard. Okay, so okay, this is the general idea, which is even if this flip distance is nicely described as the work on the skeleton of a polytope, This can be hard in some cases, for instance, selection of two-matrix perfect matching polytope. But if you restrict the definition of a flip, then sometimes you're polynomial, but that's thanks to a very strong partial order structure behind there, okay? So hopefully, I'd like this to be sort of, you know, hints on ways to study other kinds of flip graphs and flip distances, and eventually maybe give us some, you know, clue on how to tackle the associahedron question, also the rotation distance between binary trees. This was at least my initial motivation when looking at this problem. So thank you very much for listening, and here's the DOI pointer to the Algorithmica version of our paper, which just came out, at least electronically. Thank you very much for listening, and let me know if you have any questions.
Let us all thank speaker again. I'm just going to do it audio, and if you cannot do audio, push some button. And but anyway, it's time to ask questions. If you